Welcome back for the last time. Well, today we're going to conclude our video series by talking about the Lorentz transformation, or in other words, we're going to answer the question about how I can take four vectors from one reference frame and represent them in another reference frame. So we're going to start with our two favorite reference frames, the one in blue here, which are the unprimed coordinates, and the one in red, which are going to be the primed coordinates. So that I can relate these two reference frames, I need to know which one is moving with respect to the other. Well, so I'm going to let the red frame be moving forward in the blue frame. That is, the CT prime axis in red is going to show up as a world line in the unprimed frame, as a line that's moving upwards into the right. Right? So this is saying that something that's at rest in the red frame is moving to the right in the blue frame. Now we know from our studies of special relativity that if I do this relativistic transformation, then the CT prime axis is not going to be parallel to the CT axis, and the X prime axis is not going to be parallel to the X axis anymore. So now I can start to visualize what it might mean to take some vector that, say, exists in the red plane and transform its coordinates or transform its components so that I can write down that vector mathematically in the blue frame. Right? Because if I take some vector over in the red frame, it's going to have a different value of CT and a different value of X. Its X and CT components are going to be different in the blue frame than they were in the red frame. So to build this, I find it easiest to start with vectors that are simple and straightforward. That is, it's easiest for me to think about transforming the unit vectors because I understand how those, the direction of unit vectors, and to see how a unit vector might transform when I move it from the red frame to the blue frame. So consider the unit vector in the time direction in the red frame. So in the red frame, the unit vector for time is just pointing directly up, and it has unit modulus. Looking at that vector in the blue frame, I can see it's going to be along that world line that was defined by the CT prime axis, right? But it's not going to have infinite length, right? It's going to be some vector of some fixed length, but it's going to be pointing upward and to the right. And therefore, it's going to have a component in the CT direction, and it's going to have a component in the X direction, right? So this is the first indication that space and time are really folded into each other and that this transformation is going to have to mix up space-like and time-like things. So the unit vector, in the time direction in the primed reference frame, is going to be a linear combination of the unit vector in the time direction in the unprimed frame and the spatial directions in the unprimed frame. So that I can sort of think about it more algebraically, I'm going to call A, for now, the length of the vector in the CT direction in the unprimed frame, and B, the length of the vector in the X direction. And so CT prime is going to be A CT plus B times X, right? I'm writing the CT prime vector as something times T plus something times X, right? I'm building that vector in the unprimed frame. Now, if I go back to my spacetime diagram, calling it A and B is fine, but I actually know that there's a relationship between A and B because the slope of this line, the slope of the world line of the CT prime axis, is determined by the velocity of the primed frame with respect to the unprimed frame. Right? So the ratio of B over A is actually set by the velocity of the red frame with respect to the blue frame. Right? So I could go back to saying, well, the ratio of B over A is the tangent of the angle between the two, the T prime and the T axis, and then I could say, oh, well, the tangent of that angle is actually equal to beta, the velocity divided by c, right? But we remember this relationship just by sort of thinking graphically about what's going on in the spacetime diagram. So this produces an additional constraint that says that B must be equal to A times beta, and therefore CT prime has to be equal to A CT plus A beta CX, right? So that there's really only one free parameter left, right? You can kind of think about it as, well, the sort of length of that unit vector in the unprimed frame, where that length somehow is determined by the interval. Okay, but I can see now that I've written the CT prime as a linear combination of t and x. The only thing we have left is to find out what A is, right? Because that obviously can't be something that's unknown, because I must have a way of being able to define what a unit vector looks like in a different reference frame. And for that, we're going to now turn to what we know about the star product, right? If I look at this definition, I can star the left-hand side with itself, and I know what that answer is going to be, right? It's just going to be c squared, because it's just in the time direction. Which means that I can also star the right-hand side with itself, and that also has to be equal to c squared. And that's going to provide the last algebraic constraint, which is going to give me the ability to solve for what that A has to be, right? So far in this picture, what I've done is I've used sort of Euclidean geometry to relate A and B, but I'm going to use the invariance of the interval, that is the invariance of the star product, in order to relate A to some physical parameter in the problem. Now the algebra for that isn't hard, but I've written it out here, so I know that CT prime star CT prime is just going to be c squared. At the same time, I know that the right-hand side starred with itself has to be equal to c squared. I get an algebraic expression for A, which I can solve, and I get that A is 1 over 1 minus beta squared. Well, heck, that's just the relativistic factor gamma. Right? And so this gamma appears once again as a way of understanding how lengths transform when I go from one reference frame to another. Right? And so when I do this, I get just that that t prime, or ct prime, is going to equal gamma ct plus gamma beta cx. Ta-da! We're done. Right? And so I've been able to now transform the unit vector in the prime coordinate system into what the vector would look like in the unprimed coordinate system. So let me go back to this picture, because now I'm all set to solve for what the transformation of the x prime vector looks as well, right? And I can remember that this transformation is symmetrical about that 45-degree line. So where the CT prime unit vector got, distorted by moving a little bit to the right, the x prime vector gets distorted by moving a little bit up. And therefore, I can write down very quickly what I know this transformation to be, where I'm going to have this gamma, and that gamma is going to modify the x direction, plus a gamma beta times the time direction. You should convince yourself of the algebra of this if the symmetry argument isn't clear to you. It's reproducing the Euclidean geometry that we did before, plus looking at the interval of the x prime. Now you can see that when these two are the way that we would normally write the interval, right? Because I have my good coordinates here in the same units are x and t, but in practical applications, we often leave the c off the t prime coordinate as well. It's just a convention thing to make them look a little bit similar to each other, even though when I do it without the c in the first expression, I'm really doing these two expressions in two different units, right? So the c allows them both to be in meters, whereas if I eliminate the c from the time one is in seconds and the x one is in meters. But now I have a well-defined translation for t prime and x prime, which means that I can transform any vector that I want to. Once I know how the unit vectors transform, then I can take any vector and write how that vector is going to transform. It's also important to note that beta, as it appears in this transformation, is also a vector, right? If beta is positive, that means that the red frame is moving to the right. But if beta is negative, that means the red frame is just moving to the left, right? Which is, of course, the old transformation, which went from the unprimed frame to the prime frame, right? So when I write down the transformation of the unit vectors, I might want to go back to my spacetime diagram to make sure that the sign of beta is correct. But how I've written it here, with the prime coordinates going to the right in the unprimed frame, I have a transformation for my two primed unit vectors in terms of my unprimed coordinates, which I can then redefine as the transformation for the two unprimed unit vectors in terms of the primed coordinates. And that minus sign that appears in the algebra that you would have to do to combine these equations is exactly the same statement that you can just switch the sign of beta if you think about the reference frame going in the opposite direction. Okay? So the only thing that can change signs when I go from one coordinate frame to the other is the sign of beta, but I have to be careful about which frame is actually moving with respect to the other frames. For me, it makes most sense to think about, in the spacetime diagram, which frame is moving to the right, and therefore, when I draw the unit vectors in that frame, are they pointing, to the right on the spacetime diagram, or are they pointing in some other direction? Okay, well, that's how unit vectors transform. And I know that that's a very powerful idea because if I write down any vector in terms of its unit vectors, I can now just plug in the new unit vectors and I can get that vector in a new system. So let's do it for some arbitrary unit vector that arbitrary 4 vector that I'm going to call A. Okay, so I have A, and I have A's components, AT and AX, in the unprimed reference frame. Well, I can use the unit vectors that I just calculated to transform this vector from the unprimed frame to the primed frame. That is, I'm going from some frame to some other frame that's moving in the positive direction in that frame. And all I have to do is plug in the unit vector t and the unit vector x, and I get and I can go through all the algebra, and I get now that there's some new time-like component, and there's some new space-like component. That is, A, expressed in the t prime and x prime coordinate system, has information that used to be in the t and x components of the original vector. That is, A, as in the unprimed frame, when I move A to the primed frame, both the t and x components change, and they exchange a little bit of information with each other and some information about the relative velocities of the system. So as it's written now, the going from some frame to a frame that's moving in the positive direction with respect to that frame, I've been able to rewrite the vector A in terms of the unit vectors of the new frame, and therefore I have transformed A from the unprimed coordinates to the primed coordinates. I want to make sure that we kind of understand the difference between this and what we did before. What we did before was we wrote down a unit vector and we transformed that unit vector from one reference frame to another. Here, I'm taking the components of a vector in some frame, and I'm saying what are the components of the vector in the new frame. Right? And so the piece of information that I'm getting is slightly different than the information that I had before. But of course, there was nothing special about A, and so I can apply the transformation rule that I just derived to any vector I want at all, and the one that we always apply it to first is the location vector, which we call sigma, which of course has a time component that's equal to ct, an x component that's equal to x, a y component that's equal to y, and a z component that's equal to z. Well, I can plug this into my transformation, and I can get, in the new frame, then the t component, which is ct prime, is going to be gamma times the old t component ct minus beta gamma times the old x component, which is just x. That the new x prime coordinate is going to be minus beta gamma times the old t component, which is ct, plus gamma times the old x component, which was just x. And heck, why not just do y and z while we're on a roll? Well, nothing's moving with respect to y or z, and so those two things don't change. In this set of 4 equations, then now, the vector that I transformed was the position vector, so what I've calculated are, what are the new components of the position vector? That is, where is it in space and time in the primed frame, based on where was it in space and time in the unprimed frame. And this combination of expressions is what's traditionally known as the Lorentz transformation, because it tells me how components of the position vector, where are you, transform when you go from one reference frame to another. That is, what are the components of the position vector in the new reference frame based on the components of the position vector in the old reference frame. Okay, we've covered a lot of material, but at its heart, it's things that we've been doing all the time. We've been doing it, since we first learned about coordinate systems. We're just doing it for a coordinate system that we're a little less familiar with. We found out that we can transform unit vectors, and that I can write down unit vectors in a new reference frame based on what I understand of unit vectors from an old reference frame. And we did that graphically using the spacetime diagram. From that, I can also say, well, if I have the components of a vector in some reference frame, I can calculate the components of that vector in a new reference frame. And that works for any good 4 vector, and therefore it has to work for the good 4 vector that represents the position. And when I do it for the position vector, I call that the Lorentz transformation. But it works for any 4 vector. If you have a good 4 vector, you can use the transformation properties that we derived in this video to find out what the components of that 4 vector are going to look like in any reference frame that you want. Well, this has been a lot of fun. I hope you've enjoyed taking the Fields in Spacetime class with me. So long.